Hey folks, welcome to the first tutorial of the Trie playlist where we are going to discuss um, like right from the basics what a trie is, why is it used, what's so good about it as a data structure, and then we'll move on to solve problems in the upcoming tutorials. The problems will vary by the difficulties, and we are going to really solve some really interesting problems that highlight the use of the trie as a data structure. So let's get started with the first tutorial. So the first tutorial, I think it's gonna be more towards explaining what a trie is and why is it really needed, and we are gonna look at so we are gonna make a trie. We are gonna look at its operations, the basic operations that it supports. We're also going to have a look at the time complexity of those operations, and we're also going to analyze the memory complexity that the trie uses when it's being built or when it's built. So yeah, let me just type out the word trie first so that we are actually, you know, we are officially started. So trie is kind of, it's derived from this word, retrieval. So just to give everybody some context on why is it, I mean, why is it called a trie? Why is it weirdly called a trie? So it's it's kind of used as a middle syllable from this word. So as it says, as the word says, retrieval, uh, we can we can assume for now that this data structure is mainly used to make to analyze or retrieve data quickly. Okay, and yeah, so that's about the word trie. And before we move on to discuss what a trie is, what it can do, and its operations, I would like to start with a really basic problem where we say that, hey, this is the problem, and how what's the first approach that comes to mind when you think about it. So let's get started with that problem first. So let's say, let me zoom in a bit. Yeah, looks good. Okay, so we have an array of strings and it contains n such strings. Let's say the array looks like this: s1, s2, s3, s4, so on till sn. Okay, and we also have a string p. So check if p exists in the above array or not. So this is a pretty standard problem, and I mean it's also a really interesting problem when you first look at it. So um, the first approach that comes to mind is the naive brute force approach, where we say that for all the strings s in your array, let's call this array string array, I think. Yeah, so for all the strings in the string array, if your s is equal to p, return true. Outside the for loop, if you're not return anything, then it should not exist. We should return false. And let's say everything is inside your function. Pull check existence, something like that. Okay, so this is the naive approach that comes to mind, that comes first to mind. And complexity would be like, since you're iterating over the entire array of n strings, this is O of n, and each comparison, so string comparison between two strings takes this complexity, minimum of length of s comma length of p. Since when you write a double equals operator, it essentially checks every character in both strings up till their minimum lengths, since there is no point in going further in a string that has exceeded the minimum length of the other string. So that's why it's of minimum of their lengths. So if you, I mean, because this comparison is inside a for loop, the complexity would become of n into l. Let's say this is the worst case, which occurs when all the given strings are of equal length l. So now we are good with the worst case here, but this is a bit of a problem for us because let's say n is really big and your l is, let's say n is, let's say 10 raised to 5, your l is like l is also big, I think, then this becomes kind of a problem for us, and we want to come up with something better. So basically, as is the nature of most strings problems, what we want to do is, what we want to avoid is naive string comparison, because this step takes a lot of time. This is the bottleneck step, and we want to remove this comparison somehow. And right, so how can we do this? There exists a way called string hashing, which we are not going to discuss here, but basically the idea is that convert every string into a hash. Hash is basically a number, and then do comparisons between numbers, which is essentially O of 1, right? So this way you can speed up the comparison process by converting every string into a hash, and then do a lookup based on the hashes that are provided. So that's one way to do it. But let's say I modify this problem a little bit. The only modification I make is that instead of checking if p exists entirely in the above array, we want to check if p exists as a prefix in the above array. So this is one modification we want to make to this question. We want to check if the p exists as a prefix in the above array. So then naively I think the complexity would be cubic, and that's what we want to really avoid. And using string hashing, we still have to check the prefix hash and compare it with our string p. So we still have to go to every prefix, we need to have its hash. Let's say we want to try to pre-compute its hash, we still need to compare those numbers as prefixes with our string p, which is also hashed, right? So, and this is also a lot of comparisons because we are going to every prefix individually of that string, and then we want to check, and then we're comparing the hash string p. So we want to do better. So for these kind of problems where you're given some big array of strings, you're given some constraint on those strings, and then you said that do some analysis on the strings, and these kind of problems, and we'll come to problems later, but I mean we discuss real uh, coding problems later in the upcoming videos. But now is a good time to introduce the trie data structure. So all right, let's talk about a trie now. Trie, yeah. So essentially a trie is a tree. Remember this. Okay, trie is a tree. So tree is basically a data structure which has n nodes. It's a graph which has n nodes and n minus 1 edges, and it doesn't contain any cycles. It is acyclic by nature, and yeah, that's basically a tree. So trie is a tree, and so as a tree contains a root, a trie also contains a root. Let's say this is the root of the trie, and now let's say its corresponding children are these, and it is an n-array tree. N-array tree means like it can contain n number of children per node. So let's say this root node contains 4 children, for example. This one went a bit far. Okay, this is your root. So when strings are concerned, so here we'll talk about lowercase strings, only strings which contain lowercase alphabets. Okay, so in a trie, each of these links are references to their particular trie nodes. So these are called trie nodes. These are called links. We'll call them as links. So these links tell us to what trie node we want to go to. And since we are considering only lowercase alphabets right now, these links have the references of the lowercase alphabets. So let's say A goes here, B goes here, C goes here, D goes here. Now I'll come to how exactly I put an alphabet on a link. So it doesn't even make sense when you first look at it. You're just saying I'll be putting A on this link. I mean, like, what does it even mean? Why do you put A here? So to understand that, let's first look at what is inside a trie node. Okay, this is your trie node. Inside it, you'll have an array of 26 characters because there are 26 lowercase alphabets, right? You'll have an array of 26, length 26, and you will have some bunch of extra variables here which we don't need to worry about right now. We'll come to that stuff when we talk about the real problems, but for now, let's say you have this array, and let me expand this. So this is your 0, 1, 2, 25, right? This is your A, B, C, and Z. Dot, dot, dot. Okay, so each of these boxes contains an address to the trie node linked by the alphabet. So in this case, it contains the address of the trie node to which A, so A is in the A alphabet, will take us to. Okay, so that's the reason why I put A on top of the link, because we know if we traverse this link, where are we reaching? So when you traverse the A link, you'll reach a trie node that is being pointed by this A, and similarly for B and C, and for D as well. So this is what this array will contain, right? It contains the address of the trie nodes linked by the alphabet, which you are looking at. Okay. So now that's clear to us, we can go ahead and you know make a trie. Yeah. So let's say one more example I will take here is that, let's say the array of string is apple tree, apple, apple juice, banana. I mean, I took two big words. Let me take smaller words. Let's say it's app, app v2, a, abc, b, and bj, I think. Yeah, so some random words, and we want to make a trie out of these words. Okay, so first, as always, we'll make the root node. Yeah, so the root node will initially tell us where we want to go. So now let's say I want to first insert app in the trie. We want to insert words one by one in the trie. Okay, so now I will insert app. So since initially only the root node will only create the root node, so now there is no inside this array that this root node will contain, everything will point to a null reference. Everything will point to a null reference. That means that no nodes are originated out of this root node. So since we want to insert app, we'll first look at A, and we'll say since A is not created, create a node which will point to A. Okay, so now this guy has an address. This is basically A, B, C, D, T, Z, dot, dot, dot. Okay, then and now when you are inserting words, you will create a trie in a depth first fashion. So now you're standing at A and you're seeing P. So P is not created. So let's create a trie node pointed by P. Okay, and again there's a P in app, so let's create that as well. Okay, so this will represent how your app is inserted in this trie. Okay, now we have app v2. So we'll again start from the root node. We'll say, okay, A is created. We don't need to create A again because A already has a reference to P. Sorry, to a new trie node. And in app v2, we go to P and we see that P is also again created. So we jump to the next character, which is again P. So we again see that P is created. And now we jump to V. So we see that from this trie node, there exists no reference to a V. So what I mean by that is, this will again contain its own set of characters. Everything will be null because this guy doesn't go anywhere, right? So the V will also be null. So we will slide somewhere over here. This guy will also be null. Okay, so this is just for demonstration purpose. Okay, so now we'll create a V node from here. Okay, and then there's a 2, so app v2. And I also promised you guys that we'll use only lowercase alphabets. So let me change this app. Oops. Let me change this app v2 to app v2. Okay. So just insert app v2. Okay, none of these guys are created. Okay, let me reset the zoom. Oops. Okay, now we have A again, we have A, and then we have ABC. So A is created, but from A there is no B. So we need to create a B over here, right? And then we'll create a C, because for this B there was no C. It was none actually. And then do you have a B which is starting from the root itself? So we know that from the root this B is pointing to a null reference. So we will create a node, and this node from the root B will point to this particular node. And then we have the last word as bj. So since from this B there is no reference to j, we'll create that reference to j. Okay. So this is how your trie will look like for this set of strings. Okay. So having sorted that out, I think what we can do now is look at analyze the complexity of the basic operations of a trie, the time complexity, and we'll then later at the end analyze the memory complexity. Okay. Now we'll talk about, we zoom in a bit again. Time complexity of basic operations in a trie. So it's pretty simple to analyze them. Creation of trie. So when we want to create a trie, first, instead of talking about the creation, let's first talk about insert, since it's more atomic by nature, and we can use multiple inserts to create a trie, right? So we'll first talk about insert, and then we'll talk about the complexity of creation of a trie. So insertion. Okay. So for a word of length L, we need to at most create L nodes, and so the time complexity for insert for this word is O of L, right? So time complexity for insert for this word is O of L, and now we can talk about the creation of a trie. So now we want to insert n words in a trie. Yeah. So let's say each of the lns is L1, L2, L3, Ln, right? So generally it's like n into L1 plus n into L2 plus so on. But the thing about this is that we don't know how many overlaps will each trie node contain. So but this is a upper bound, and when you're actually implementing the problem, the actual runtime complexity will be much less. We are just trying to see a reasonable upper bound of a creation of a trie. So this is, if you refer to Wikipedia articles or if you refer to some DSA books, what they'll say is it's O of n into average length of all strings in the array. Let's call it L average. Okay, so it's O of basically O of n number of strings into L average. So we just want a number which we can tie to these lengths. We are just taking the average of them and calling it L average. So this is the complexity of creation of a trie. Now for searching, so remember when we started talking about the trie, I told you guys that trie is basically a tree, right? And the most efficient way to traverse a tree is by using depth first search or DFS, right? And when you use DFS, you have some particular target in mind, saying that I want to, let's say, find the lexicographically smallest string, or let's say I want to count the number of words which have a certain prefix, something like that. So that's the nature of most trie problems. So you need to think on how you will actually traverse a trie. You need to modify how you will do your depth first searches, etc. But the idea remains the same. You basically use some sort of depth first search or some modification of it at least to traverse a trie. Searching is basically searching, you can also call it, or traversing the trie, and this can be done, and again, of max height of the trie. So max height of the trie, so in this case, if I scroll up, max height of the trie is represented by this word ep v2, which is nothing but 1 2 3 4 5 6 7. So this word is like 7 levels deep, right? That's the length of the word. So max height of the trie is nothing but of max length of the word in the array of words, array of strings. Let's call this string as well, of the string in the array of strings. So it's basically O of L max. Yeah. So this is basically, the searching operation is really good and it's really efficient. So you'll come to get more insight when we solve the problem. But yeah, it's, for now, let's just assume that it's really efficient, it's really fast, and it runs in a complexity of O of the height of the trie. Okay. And talking about deletion is basically just undoing insertion, right? So it's again, since insertion was O of L, which is the length of the word L. Deletion, when I say deletion, I mean that delete a word L from the trie. Word, let's say word W of length L from the trie. So it's just basically doing the insertion process. So it's again O of L, the length of that word. Cool. So that was about the time complexity of the basic operations in a trie. Now we will now move on to talk about the fun part, which is the, just a second, yeah, which is the memory complexity. So before we dive into calculating the memory complexity, what I would like to do is calculate the number of nodes in a trie. So how many nodes? So let's say given an array of strings up till Sn, how many nodes find a upper bound on the number of nodes that are created for the given array of strings, right? When you make a trie, and let's say every string has only lowercase case letters. Okay, so basically 26 is the character size. Okay, so when you think about it, since we talked about average lengths, okay, so let's say the average length of the word in the above array is 1. So what that means is you will only have one root node and you will only go one level deep in the trie. Dot dot dot. Okay, like this. You know, your A, B, C, and whatever here. So you'll only go one level deep. So in this case, the number of nodes can be written as minimum of 26 comma your L, sorry, not L, N into 1. So 1 is your L average, right? The average length of the word is 1. So since there are n words and the average length is 1, so basically every word occupies only one character, you can have a maximum of n characters, right? At this height, at the height of 1. So the number of nodes in this case is minimum of 26, which is the number of characters that this trie can hold, with the number of nodes, which is n, or the number of characters, which is n. Yes. Now let's say your L average, this average length of word, is 2. So in that case your trie will look like this, and let's say something over here, and then again you will have 26 reference. You might have at max 26 references for this node. Similarly for this one, you will have 26 references, dot dot dot. Similarly for this one, 26 references. So at this level you have 26 nodes. At this level you have 26 square nodes. So the number of nodes in this case would be minimum of 26 plus 26 square, comma, since now each node also occupies an average of 2 characters, so the number of characters would be 2 times the number of words, which is n, right? So minimum of this expression, comma, 2n. This will be the number of nodes in this trie, right? So we are just, it's not an exact count, we just want a reasonable upper bound. Okay, so this is a reasonable upper bound when you talk about a trie which has an average word length of 2. So you see where I'm going here. So let's say now we'll talk in more generic sense. We will say that, let's say your L average is just L average, right? So your number of nodes would be minimum of 26 plus 26 square plus 26 cube plus so on, 26 raised to L average, comma, n times L average. This will be your number of nodes in the trie. Okay, so this is nothing but minimum of 26 into 26 raised to L average minus 1 divided by 25. So I'm just doing a sum of this geometric progression, and this guy still holds n L to L average. So we can nearly write this as minimum of, I think, uh, in terms of complexity, is just O of min of 26 raised to L average plus 1, let's say, and L average. Okay, so this is the number of nodes in a trie. And if, let's say, instead of using 26 characters, let's say we use a character set which has total alpha characters. So let's say it contains both lowercase and uppercase, for example. So that character set will contain 52 characters, which will be A to Z, and then capital A to capital Z. So in a similar sense, let's say we have an alpha character set which contains, let's say, alpha characters. So in that case, we can make this formula more generic. Number of nodes in the trie would be O of min of alpha raised to L average, comma, n into L average. This would be a number of nodes. I mean, an upper bound on the number of nodes in the trie. Okay, but still this doesn't tell us the memory complexity, but we can definitely come to the memory complexity from this expression. So now, we also know that each node contains an array of references, so that we know from this particular node which nodes are accessible, right? So we can look up this array of references, and we tell that, okay, let's traverse to this node if it's not null, and if it's null, we say that that particular node is not traversable. So the size of this array of references is so for lowercase letters it was O of 26, and for a general character set containing alpha characters, it's O of alpha, right? So a memory complexity would be this O of alpha into number of nodes, right? Because every node contains an array of length alpha. So then you just need to multiply it with the number of nodes to calculate the total memory complexity. And your number of nodes we just derived here. So basically you just multiply alpha in this expression. So it's basically O of min of alpha into L average plus 1. I mean, it's just call it L average when we are talking about complexity. And this will be n alpha n into L average. Okay, so this will be your memory complexity when you create a trie. So I hope this clears things out on how many nodes the trie contains and how much the memory complexity of the trie will be. So typically in problems you only need to worry about this expression. So this expression should not be too big, and it should ideally fit between in the memory limit, and if not, you need to optimize your trie to fit into the memory limit. Right. So now we'll just talk about one last thing, which is the applications of a trie. So we just talk about the applications of a trie. So trie is a really widely used data structure, and it has a lot of applications. So just to name a few, the first one that comes to mind is the autocomplete functionality that you use in Google or Google search, or on your iPads or mobile phones. The autocomplete functionality basically highlights the way a particular word is completed out of its dictionary. So your device will contain a dictionary of words, and when you type some prefix in the search bar, it will predict what word is available in the dictionary. So let's say you just typed apple, and in the dictionary apple tree was also available. Then it will show that it will highlight the tree part of that apple, and it will say apple tree is available. Do you want to type in that word automatically using tab or something like that? So you will understand more about this functionality when we actually start coding some real problems on tries. Second is lexicographic sorting, which we also call as radix sort. So this is also really well known and a good application of a trie, and we will also cover this problem. Third is I think web crawling, where we store URLs in trie nodes to have a fast lookup when we want to web crawl on a search engine, right? So there is a Wikipedia article on web crawling and how tries are really helpful. So I'll attach a link to that article in the description, and maybe you can have a look on how it's actually implemented. It's a good read. And I think there's also spell checking, which can be done using trie. Spell checking is basically just, saying that out of a dictionary of words, if you put in a incorrect word or you typed in incorrect spelling, it will say that this particular spelling does not exist in the dictionary of words that is provided to that device. So that is basically the idea of spell checking. So it is just a use case of a trie where you say what word doesn't exist in the trie, and you just prompt the user that that particular word doesn't exist. Your spelling is wrong or something like that. So these are only some major applications of where a trie is used. So, and yeah, I think we have covered pretty much everything that we wanted to cover for the basics. So yeah, see you guys in the next video, where we'll start talking about problems and we'll start solving some real and really good problems. So yeah, thank you for watching, and bye.